This is cpe225, lecture 21. We're going to review some of the architectural issues we talked about last time, and then we're going to talk about some of the important C programming concepts. And so, first of all, we all write code. Sometimes that code's hardware. Sometimes that code is firmware. Sometimes it's software. So if we're writing for a general-purpose computer system, meaning our code's going to run on multiple computers, it's going to be software. Typically, if you write for a specific piece of hardware, it's going to be firmware. The big issue here is embedded systems are practically always firmware. Memory itself, we kind of divide it up into different categories here, and we consider levels of memory as well as RAM versus ROM. So in any computer architecture, we have different levels of memory. The lower levels of memory are faster, they're more expensive, relatively small, and they eat up more power. The higher levels of memory, slower, cheaper, there's more of it as well. Main type of semiconductor memories that we deal with is RAM and ROM, random access memory and read-only memory. Turns out that both of these devices are actually random access. Random access means that I can get any piece of data out of that memory in the same amount of time, which is not true of a hard drive or a tape drive. Semiconductor memory is taking over things like hard drives. It's just better than a mechanical drive. In the end, our memories fall into the two categories of RAM and ROM. RAM is readable, writable, and it's volatile, meaning I take the power away, I lose the data. ROM is readable, it's not writable, and it's non-volatile. You take the power away and you get the power back there. So think of a thumb drive. You pull it out and the data is still there later, although you do write it, but the overriding factor is the data is still there when you remove the power. Memory signals here, there's three types of signals. There's data that's coming in and out of the thing. There's an address. The address is which pieces of data you want to work on. It's analogous to an index in an array associated with a higher level language. There's also control signals, which we need to tweak in various ways to get at the data. Memories don't typically output a bit. They're typically word-oriented, which is the smallest chunk of memory I can access in that thing, but whether it be reading or writing. These memories are considered word-oriented, where the word is not really defined. So the capacity of these memory, we usually specify them in bits, even though they're word-oriented. And another term here is memory bandwidth, and it's a rate at which you can access data in this thing. So the notion of memory bandwidth is it takes time to charge capacitors and all that stuff, or all that fun stuff at low-level hardware that no one wants to talk about. The big issue is computers move a lot of data, and typically they have multiple devices accessing memories. And if two memories try to access data at the same two devices try to access memory at the same time, one of the devices isn't going to be able to access the data. It's going to have to wait. And that's going to take a hit on the throughput on this thing. So you would think that, hey, I'll just bump up the clock speed, but you bump up the clock speed, the faster memories are more expensive, and of course, they eat more power. Two types of architectures out there, Harvard and von Neumann, also referred to as Princeton. And the notion of Harvard architecture, it has a separate memory for data and instructions. Von Neumann architectures have one memory for both data and instructions. This is usually considered Harvard's better because it's, it's one of the issues is that we don't see this in RISC-V, but sometimes the data width is different than the width of the instructions is different from the data widths of general memory. There's also Harvard architecture does better with memory bandwidth issues because there's two memories rather than one. Smaller memories are generally cheaper, and by God, it supports pipelining. And you'll see later that RISC architectures also support the pipelining in this. Two classes approaches to architectures are RISC and CISC. RISC Reduced instruction set computer, CISC, complex instruction set computers. Notice that these have nothing to do with the number of instructions in the computer. They have to do with the complexity of the instructions. So typical characteristics of the RISC computer. Simple instructions. The instruction words are all the same length, and typically those instructions execute the same number of clock cycles. RISC processors, RISC architectures generally have a large register file. Register file holds general purpose registers, and RISC architectures generally have very few addressing modes. You'll see in CISC processors they have many, many more addressing modes. Really fancy, but those addressing modes require more hardware. Generally speaking, the faster clock speed in a RISC computer, and that doesn't really mean anything. It really matters what the hardware is doing. So characteristics of RISC of a CISC is essentially opposite of all those. Okay, in the end, other things to note. RISC is often referred to as load store architectures. What you see in CISC processors is that instructions can access memory, operate on it, and write it back to memory in one instruction. You don't really see that in RISC. We have to use instructions to get out of memory, use another instruction to grind the bits, use yet another instruction to put it back into memory. Yeah, so the notion is RISC generally has less hardware. So it requires more instructions to execute, to do the same operations as a CISC computer. Pipelining is, once again, much easier in a RISC architecture, which is something we talk about later. And in the end, CISC architectures, you use less instructions. The hardware is more complex, and the clock rate's slower, but you generally get more done per clock cycle. RISC programs have more, essentially more instructions to do the same thing, but generally speaking, the clock cycle operates faster. CPU, these are definitions. It's essentially a CPU and data path, and I don't even, there they are written down there. You can read them, but the notion is that I don't really test on this stuff because I forget these as well. And the issue is I understand the hardware, and I understand what I need to know, but these are just extra things that I just very quickly forget. Okay, so we're into the C programming here. Okay, so C is a really old language. I think it was developed in the early 70s maybe, and that was the days when the programmer was in charge of everything. Everything having to do with the program. It's very primitive. It was necessarily low level, and for that matter, it still is. And by all means, it was not object oriented. So the modern programming languages have abstracted some of the operations quite high on this thing, and they put a lot of functionality into the compilers as well. So the essence is a lot of the programming responsibility was taken away from the programmer. Okay, C programmer, it's very primitive, but the programs you write are generally small and fast compared to higher level languages. And that's the good thing, or for better or worse, programmers have complete control of the programmers. It's not magic stuff done by particularly the compiler, or the compiler oftentimes generates a bunch of extra instructions. For example, C++, which is the only operating object-oriented language I know, allows you to write really highly organized programs, but it comes at a price. And the example I use is dynamic binding, and makes your program look pretty freaking smart, but it generates a lot of extra code. So the programs are usually quite large for what they do, and because they're large, they are slow. So it's totally unfit for embedded systems because it runs so slow, and the amount of code is just large, and it's even a fast processor is not fast enough to overcome these limitations. So in the end, this is important. All these programming languages roughly run on hardware, and through the years, all the computer hardware, they roughly share the similar architectures. It's very primitive, The architectures are really primitive on the hardware level now, which is funny because the programming languages have become very complex and abstracted. So I'm going to try to just teach you some of these concepts to write good C programs, and I think a C program that works is just not good enough. You need to write really good programs. A working program, nah, anyone can do that. So I'm going to try to relate these C programming issues to the low-level architecture and some of the programming concepts, and really most of what you'll find here is related to, we'll say, how it handles memory, and particularly, how C handles memory. So here it goes. So, okay, so the memory types out there. In C programming, you're going to do two things. You're going to write a program, and that program is going to be stored in hardware somewhere, and it's just going to be machine code. It's generally not writable. There is self-modifying code, which is something, computer geeks like talking about that a lot, but we generally don't do that. But more importantly, we have data memory, and that data memory is inherently readable and writable. What you're going to see is the C programmer or the C language allows you to make some of that memory, we'll say, just generally speaking, just kind of only readable, and we'll get to that later. So that's all you get, because it's that's all the low-level hardware supports. And it's just, it's memory. You stuffs up, you just put a program in it, you're going to read it, you generally don't write it, and you put memory. It has memory, you read it and write it. Everything else is an abstraction provided by the language itself. And C doesn't have that many abstractions, but it does have a few. Nothing compared to an object-oriented language. Or something really fancy like, I used to know Perl, and Perl was you can tell the compiler was really complicated on it. I haven't used Python or Java worth hardly anything, so I can't really comment on that, but I know they're abstracted pretty high. So program memory, yeah, it's a place to store the program. Not much to say about that. It's usually just readable. It's not generally writable. Something's going to write that memory, but after you write that memory, generally speaking, it's hard to overwrite again. So the data memory, in the end, what the compiler is going to do is make some of that memory permanent and some of it temporary. So the permanent memory is storing space for non-local variables, or I think I call them global variables. And I don't know if there's that concept in higher level languages, but for C programming, we got the concept of local and global variables. Okay, global variables are permanent in memory. It saves the spot for them. That spot does not go away. Okay, so essentially what it says is C, it just saves those in two different things. For global variables, I can also declare variables as static. So the static variables, as you'll see, are permanent as well. But temporary data memory is more important. It's used quite often, and so the notion is that we talked about this before, where data is passed to functions via the stack, and the variables declared inside functions are declared on the stack as well. When the function goes out of scope, that means the function finishes. That means the memory goes away. There's also the notion of a heap, which is essentially memory that I can dynamically allocate, essentially under program control. The notion in C is if I allocate it under program control, I have to deallocate it. So it's really easy to get a memory leak, which means I forget to deallocate memory, and essentially I'm just going to run out of heap space on it. It's quite a big problem. So no garbage collection in C. So temporary data, local variables, essentially local variables are temporary. They're passed on the stack, or they're created inside functions. So once again, there it is right there. Passing variables to functions and declaring variables in functions. All done on the stack. It's all temporary. It's all done under program control. The programmers don't really need to know that, but they should know that these variables are temporary, and it eats up some stack space, eats up some of the available extra memory in your program. And there's also the heap, blah, blah, blah. We just talked about that as well. Technically, I'm going to dynamically allocate this, and then when I dynamically allocate it under program control, I'm going to deallocate it. So the responsibilities that you have as a programmer is to write organized programs. And the programs it's not one giant file. It's typically broken up into modules, which supports modular programming. But it's also, those modules are put into different files. Okay, so a particular file has a bunch of functions in it, we'll say, for lack of a better word. And those functions are all related. So we do our best to divide this up as best we can. And we'll see more about that later. And we're going to write programs that use memory efficiently. So generally speaking, if we can make something, if we don't have to make something a global variable, we don't. We make it a local variable, and that's going to save space. And we're going to write secure and robust programs, and typically we're going to do that by hiding information wherever we can. So in the end, there's no correct way to do all this stuff. You give two really great programmers the same problem, they're going to come up with different solutions on this. So if you understand the C-based techniques in this, you're going to be a good programmer. It's not cut and dried. You need to work with it and practice it and think about it and spend time designing your programs rather than just start writing code. So when you write organized programs, this is what I was saying before, you keep all the like-minded functions inside the same file. And so you have a giant project, and what you're going to do is just recompile the code, that the files that you change. You're not going to recompile everything. Now this sounds kind of strange, but in real life, these programs are, we're talking millions of lines long. You're not going to recompile the entire program every time. It's going to take forever. Okay, and also, when you do it this way, the programs are easier to understand. And when they're easier to understand, they're easier to reuse and or modify. So another issue here is you want to control access to the permanent memory. Okay, and so if you don't need permanent memory, you don't make it permanent, and you want to hide access to you don't want to make all these variables global, because then everyone has access to them. And it brings up the classic shared data problem. I don't know if this is an issue in other languages, but when you're working with C, there is a shared data problem, which means different modules can get at data and change it when you don't think it's changing it. Once again, huge problem when you're working on a team of people. You understand what you're doing and you do it right, but other people have access to your variables if they're global, and you generally don't want that to happen. You want to write programs that manage memory efficiently, and memory in the real world is limited. It's typically highly limited in stuff like embedded systems out there, and there's everything's limited in embedded systems. Remember, there's like 20 times more embedded system computers out there than there are like laptops and desktops and those things. So really, to save space here, and you're force your program, essentially the program part, to be shorter. You don't want to be declaring a whole bunch of global variables. It will work, but all the global variables you declare, that's less space for your program. It's also, when you nest subroutines or call subroutines, you're going to eat up extra memory. That's going to take away, once again, space for that you could be using for the program. Also, in a real-time operating system where you have multiple threads of execution, the idea here is all those threads have their own stack, and it gets really big. It's really useful, but you don't want to limit how many tasks you can have in your system. And lastly, of course, this is going to support data hiding as well. Data hiding is super important when working on like a large team of people. I think I've said this a couple of times already. Is you don't want to give people access to data. And when I was working for the government, I had a secret clearance, and we had the notion of people had a need to know. If people didn't have a need to know, you didn't tell them. And the same thing works with the program. If functions don't need access to data, you don't give them access to that data. Making everything global makes things easier, but it's just a disaster waiting to happen. So permanent data is really easy to access, and global data. And if you can access it, you're going to have big problems. And there's lots of tools in C to do some data hiding, and we're going to take a look at a couple of those later. So variables in C have two main attributes, and it's the type and the storage, and that's it. Well, think about that for a second. That's the type and the storage. The storage means where you're going to put it. Generally speaking, that means whether it's permanent or not. Okay, and sometimes it's global, sometimes it's local, and those are what we're referred to as storage. So the types, there's very few native types in C, such as the int and char. But recall that a char is pretty universally 8 bits, but it's going to be operated on in 32-bit registers, so it's not super useful. And think about all the fancy types out there. Well, they're going to be manipulated by the same hardware out there. And look, there could be problems. For example, if I use floating point operations, and I don't have a floating point unit, well, I'm going to have to do those floating point operations using like integer math, and it's going to be a nightmare. It's going to take a lot of time, and it's going to take a lot of extra code. Also, if I'm having like a 16-bit machine and I'm working with 64-bit values, it's going to cause a lot of extra code to for a 16-bit machine to work with 64-bit values. So in the end, it's kind of funny because I don't care what you're doing, how fancy you get, all these things all these operations are implemented on hardware that's inherently integer based. So storage in C, it's either permanent or non-permanent, and it all depends on how the programmer declares it. So these are the 4 storage classes. Well, it's kind of confusing. We'll talk about these as best we can, but the first one is automatic, and you can declare as auto. No one ever does this. I've never seen a program that declares it auto, because essentially if you don't include this storage type, it defaults to automatic. It is temporary. It's most often used type. Essentially, the variables inside functions default to automatic, and so because they're temporary. The variables inside the function, they're inside functions. They're declared in the stack. They go in scope when the function's called. They go out of scope when the function's exited. So this is the notion of automatic variables. And it makes no sense to declare a variable automatic in a global way, and we'll see an example of that later. It's just I don't even think you're allowed to do that. Global is permanent, but the notion of an automatic is temporary. Another storage class is register. So I can declare stuff as a register, and it's a request to the compiler to dedicate a register to holding that variable. Typically, you like to think it's used for like iteration variables and that type of thing. But it's kind of weird because, sys processors have very few registers. It's hard to imagine the compiler actually giving you one of those registers to use as a variable. So it's not used much. We hope the compiler is smart enough to do this anyway. But it's out there, so it's something makes you something to be aware of. And once again, it makes no sense to make a global register, a global value, a register value. It's just, the doubtful the compiler would even let you, but even if it let you, it wouldn't comply with that one. So here's the function here. And so it's the return value is an int. These are the parameters, the formal parameters. This is what I'm sending to the function. So when in the end, a and b, and this is a variable and declaring inside the function, they are all on the stack. Okay, and so here's a register also, and it's a request to put that value inside a register, but no one knows if it really happens or not. This is just some dumb operation, no big deal. Here's return value, so it's going to return this value to the calling code, whatever that is. And once that returns, all these variables here are going to go out of scope, which means the ones that are declared on the stack are going to be gone, and the register value, if it was even given a register, is going to go out of scope as well. So permanent storage in C programming is referred to as static, kind of, sort of. The notion of static means what it says, it doesn't move. Okay, that means the storage did not go away. And so there's two versions of this, of static variables. One is global variables. They're inherently static, even if I don't put a static declaration on them. Okay, but if I declare them outside of a function, they're global and they're permanent. And they're kind of considered static, kind of, sort of, but static actually has a different definition. We'll see that in a second. So I can also declare static variables inside of functions, which you'd think would be on the stack, but they're not. And so the issue is that they are permanent. They have, you call a function with a static variable in it. You can initialize it on the first function call, and then it skips all the other function calls. And so you can only initialize it once, but all the other function calls use that same variable value. So that variable value stays persistent across calls from the same function. And I think we've got an example of that coming up here. Okay, so this variable here, it's global, and it's kind of sort of considered static, but we don't really call it static, because if you put a static in front of that, it has a different definition, and we'll talk about that in a second. These are variables inside a function. It happens to be the main function, no big deal. They are going to be stored on the stack. I mean, you can call them non-permanent, but it's kind of strange because, generally speaking, the main function does not go out of scope until the program ends. So here's a function here, and this is a static integer here. So what it is that this thing is permanent, unlike what we saw before when those variables are stored in the stack. And these are stored in the stack, but this one is not stored in the stack. There's one copy of it, it's permanent. The value, whatever I assign to this, stays in there for the next function call. And I think that's about it on this thing. Once again, A and B go out of scope. Once I return from this function, X does not go out of scope. X remains, keeps its value, and it remains there. And next I call this function again, that X has that same value. Yeah, so static, it gets worse. So essentially I can declare global variables as static, which means that those variables can only be seen in that particular file. So they're kind of global to that file only. Okay, and then so we have another type of source class here is external, and I don't really know why this is called a storage class. But the issue is that if I declare something globally, that means other functions can see it. Okay, but and that's the case. I'm not going to officially declare it in the other files, but I kind of need to tell the compiler that, hey, there's this variable out there that I'm going to use, but I'm not going to define it here. And the way I do that is by using the extern storage class on this one. Once again, it's a promise to the compiler that, hey, somewhere out there, just trust me, somewhere when I link this program together, it's going to define, it's going to officially declare that global variable on some other file. So I think these are the two last files here. So this one is what do I want to say in this one? Yeah, we've seen all this one. I should have chopped that one out. This is the one I want. Okay, so this is a global variable. And this can be seen by any other file in the program. But this is kind of a global variable as well. I declared it static, which means y can only be seen in functions inside of this file. Okay, so once again, it's a way to hide data, prevent people from accessing data, prevent functions in other files from accessing data. Okay, and then there's the fancy stuff here. So here's some other file here. And what I'm going to do is, this file happens to use an X, but what I'm going to do is use the global X. Okay, and then what this line does here is tells the compiler, when you see this X, don't panic. I promise I'm going to declare it in another file, and the compiler's happy. When it gets linked all together later, everything's happy in this one. So this X right here is going to be the X that I declared globally in a separate file, and these are stored in the stack as usual. And I think that is it. That is all I had to say. Very confusing. Once you start using this, you get used to it quite quickly. The issue is it takes a little bit of practice, and I still wonder. I sit here and wonder if things like Java and Python have these issues as well. But these are typical issues dealing with C.